In this lesson, we shall work through each of the graphs in section 4, MRJT1, Simplified Flight Planning. To start, turn to page 2, figure 4.1. Figure 4.1 allows us to determine the optimum cruise altitude to give the best fuel economy. Enter the graph with either the brake release weight, which is the weight of the aircraft at the start of the takeoff run, or with the weight at the start of the cruise. Go vertically up to intercept the cruise profile of either 0.78 Mach or 0.74 Mach. From the intersection, go left to read off the optimum altitude at the left of the graph. If it is not possible to cruise at the optimum altitude found in figure 4.1, then a penalty is incurred in terms of fuel consumption and range. For example, if the aircraft were cleared to fly at 4,000 feet below its optimum altitude, the fuel consumption in any cruise mode would increase by 4% and the range decrease by 4%. Figure 4.2 is used to determine the optimum altitude for a short-range cruise of up to approximately 230 nautical air miles track distance. The climb and descent distances are included in this, and the altitude found from the graph is one where the aircraft can maintain level flight for at least 1 minute. Using the example given, enter with the trip distance of 175 nautical miles and go vertically to intercept the ISA deviation line. This line represents ISA deviation at the cruise altitude. From this point, go horizontally to the reference line. From the reference line, parallel the nearest curved line to intercept the vertical line from brake release weight of 52,000 kilograms. From this intersection, go horizontally to read off the altitude on the right of the graph, which in this example is 28,000 feet. Figure 4.3.1a is used to determine the fuel required and time taken for a trip distance of between 100 and 600 nautical ground miles in long-range cruise mode. The following 2 pages have graphs for distances of 200 to 1200 nautical ground miles and 1000 to 3000 nautical ground miles. These graphs are identical in their operation, so we shall use figure 4.3.1a as the example. It is worth noting that this and the subsequent graphs in this section are entered using ground miles. This is because the wind component is an integral part of the graph. The example shown on page 5 uses the following figures. Trip distance 350 nautical ground miles. Cruise altitude 29,000 feet. Estimated landing weight 30,000 kilograms. Wind component 50 knots headwind. Temperature deviation plus 20 degrees Celsius. Enter at the bottom with the trip distance of 350 nautical ground miles and move vertically to the wind component reference line. Parallel the wind component line to intercept the wind component, in this case 50 knots headwind. This line will go up and right for a headwind component and down and left for a tailwind component. From here, go vertically up to intercept the chosen pressure altitude line of 29,000 feet. Go horizontally right to the next reference line, which is the landing weight reference line. From this reference line is a series of solid and dotted lines. The solid lines represent a pressure altitude of 10,000 feet, whilst the dotted lines represent an altitude of 33,000 feet and above. By interpolating the slope appropriate to the chosen pressure altitude, go diagonally up and right or down and left to intercept the vertical line from the estimated aircraft landing weight, which is 30,000 kilograms in this example. From this intersection, go horizontally right to read off the fuel required, which is 2,300 kilograms. We now go back to the intersection of the vertical line from the wind component and the pressure altitude. Continue this line vertically to intercept the pressure altitude lines at the top of the graph. Interpolate the chosen altitude between 10,000 feet and 29,000 feet and above. In this example, we can use the 29,000 foot line. Go horizontally left to the isodeviation reference line. Parallel the diagonal lines up and right or down and left to intercept the cruise isodeviation temperature line. In this case, down and left to +20. Go horizontally left, if necessary, to read off the trip time, which in this case is 1.05 hours or 1 hour 3 minutes. The graphs for all of the other cruise profiles, shown on pages 8 to 14, are used in the same way as has been demonstrated for the long-range cruise. If a head or tailwind component is too large to be entered in the graph, convert the nautical ground miles to nautical air miles and ignore the wind component correction. In other words, go directly from an input of air distance to the pressure altitude. As aircraft weight decreases, the optimum altitude increases. This greatly increases fuel economy. The standard method of increasing altitude as weight decreases is to use a step climb procedure. In order to comply with the semicircular flight rules, this is done in 4,000 feet steps. Graph 4.3.5 allows for the increase in cruise altitude in 4,000 feet steps, up to 2,000 feet above optimum. The graph is used in the same way as the cruise graphs already mentioned, except that brake release weight is used in place of cruise pressure altitude. When you are ready to continue, turn to page 16, figure 4.3.6. The alternate planning graph allows for the determination of fuel and time for a missed approach at the destination, climb and cruise, and straight-in approach at the alternate. The method of use is similar to the previous graphs. Enter with the distance to the alternate, in this case 245 nautical miles. Go vertically up to the wind component reference line. Follow the curve to intercept the wind component of 50 knots headwind. Go vertically to intercept the landing weight at the alternate, which is 45,000 kilograms in the example. Then horizontally to read off the fuel required, which is 1,890 kilograms. Go back to the intersection with the landing weight, and from there go vertically to the all landing weights line. Go horizontally left to read off the time to alternate, which gives us 0.79 hours, or approximately 47 minutes. For distances greater than 500 nautical air miles, use the long-range cruise planning graphs. Figure 4.4 is used to determine the fuel required for holding at various aircraft weights and altitudes. The pressure altitude for the hold is shown in the left-hand column, and the aircraft weight is shown in bold type in thousands of kilograms along the top of the table. Enter with the aircraft weight and pressure altitude, interpolating as necessary, and read off the fuel flow in kilograms per hour where they intersect. If you are required to calculate the final reserve fuel, remember the figures are in kilograms per hour, so halve the figure to give the correct fuel consumption for 30 minutes. If the hold is in straight and level flight, reduce the fuel flow by 5%. Whilst the method of use of the simplified flight planning graphs is straightforward, great care is required with interpolation. Use a protractor or ruler to help draw lines accurately on the graphs.